Frank. Frank will be your instructor today, at least for a period of time. So let me just tell you a couple of things about Frank. Frank's senior, graduating, next year attending Michigan State University, as you can see. Some of the things I wanted to say were, like AP Physics was yesterday. The AP test for AP Physics was yesterday. Frank took AP Physics this year, and Frank opted to not take the test, and not out of a fear that he wouldn't perform particularly well. It's one of the most, actually, for my feeling on this, one of the most impressive choices I can recall from a student making. He didn't want to take the test because he didn't want to be bothered by the anxiety that's associated with the stress that goes along. I think anyway, that's sort of my interpretation. He wanted to focus on making sure that he understood the material and just not worry about the stress of it all. I just think that that's amazing because there's a lot of well, what do I get out of this? Well, Frank chose to take nothing out of it. He's like, I'm going to do this. I'm going to take nothing. Do not give me anything for this. I'm going to do it anyway. That's just super impressive. So I have a similar class like this. My AP Physics class is 7 kids in there. And everybody is just directing themselves, and Frank does a really, really nice job of doing that. In any case, Frank, what are you studying next year?
Next year I'll be majoring in astrophysics.
Frank is going to be studying astrophysics at Michigan State. I've just been interested in physics for quite a while. Nothing's new going on. Well, at least in the classical physics world, there is nothing really new here. In the world of physics, there's a lot of new things. There's nothing particularly new. But the same idea from a different set of lungs might just do the trick. So Frank's going to talk to you a little bit about work.
Yep.
All right, so have at it.
All right. Now, I just want to start off by saying that this is sort of unfamiliar to me. I don't tend to talk a lot. So being in front of people, even if it's only 5 or 4 people, it can be a little difficult. I'm going to have my notes with me to guide me through what I'm doing. So if I refer back to them a lot, I apologize. I just want to make sure that I stay on track and don't make any errors.
Yeah. And so to that end, the other thing here is, I think that Frank actually recognizes, he came to talk to me about this as an opportunity or something that he was interested in doing. He recognizes that this is not, probably this is the best practice to find out how well you know something, is to try to teach it in front of a bunch of people that you do not know. So this is, even though very kind individuals, there's a little bit of stress associated with that. So make it look have your pencils out and take notes. I will not do any more talking. So show your respect, all that good stuff. I'll listen.
So, to start with the basic work equation, I'm going to start over here. So, as I'm sure we all know, work, let me use this one.
Yeah, there's some that are, red's usually better.
Is there an eraser?
The towel on your right, that's hanging. That towel. Perfect.
So, work equals force times distance times cosine of the angle theta. We all know that, I'm assuming, correct? All right. So, this angle theta, is someone able to tell me what this angle theta represents? If not, that is okay.
It is the angle that the force is acting on versus where it's moving.
Yeah, so it's the angle between this force and the direction of motion of the object. So if I have a block right here, and let's just say we have a force F of 50 newtons acting on this block, and the block moves 12 meters in this direction. What I can do is, in this direction of motion, let's say there's an angle theta right here. So it's moving in this direction, and the applied force of 50 newtons creates an angle theta in the direction of motion. Yes.
Is that the only force that is acting on that object? Is there only a 50 Newton force acting on that object?
No, there's a multitude of forces that could be acting on this object.
Okay.
However, just for this first example, I want to focus on the work done by this force.
Gotcha.
Right? So, let's say this angle theta equals 30 degrees. So that means the work done by this particular force on this block equals the magnitude of this force, which is 50 newtons, times the distance or displacement, which is 12 meters, times the cosine of this angle, 30 degrees. And then if I plug that into my calculator, or Mr. McDonald's calculator, 50 times 12 times cosine 30, equals about 519.6. So let's just call that 520 joules. So this force of WF is 520 joules. Okay? Do we all kind of get that? Alright, yes.
Use the word magnitude.
Mhm.
What do you mean?
The magnitude?
Yeah.
Well, this force is 50 newtons. I said magnitude, which just refers to the distance from 0. Now, this isn't negative, so I could have just said force equals 50 newtons, not just magnitude of force.
Okay.
Alright.
Question.
Yes.
What's a joule?
Joule is the unit that we use for work. Alright. So, as Mr. McDonald pointed out earlier, there could be a multitude of forces acting on this block. There could be a weight, mg. There could also be a normal force. And then let's also add a force of kinetic friction. Let's say the mass of the block equals 4 kilograms and the coefficient of kinetic friction equals 0.2. Yes.
Why is there a normal force? Are you making an assumption about where the object is located?
Well, if we assume it's on the surface and it's not accelerating upward or downward, then there is a sum of the forces in the y direction is 0. So therefore.
So it's not floating in outer space?
No.
It's sitting here on a table somewhere?
Yes.
Okay.
So I should clarify that it is on a surface, it's not just floating somewhere, yes.
What is it on?
The normal force is the force that acts in the opposite direction of the surface on which the object is floating. So it doesn't always have to be pointed straight up. If it were on an incline, it would be perpendicular to that surface.
Okay.
Isn't it kind of like the force, like since it's sitting on something that's like holding it on so it's not just going down? It's like
Yeah.
the table's kind of putting that force on it.
That's
so
exactly how I would think of it. Like, it's like the table is the thing that's doing the normal forcing. The table is like
As if there wasn't any
doing
normal
the
force
balancing act
falling
here.
through, but the normal force is like from it sitting on the table, that's what's keeping it up so much. It's not like,
So as we did with this force F of 50 newtons, we can find the work done by each of these 3 forces. So let's start here. So if I wanted to find the work due to gravity of this object, which, again, let's clarify, moves in this direction, a distance of 12 meters. That means I want to find WG, the work due to gravity. Now, since gravity is the force we are trying to find the work for, our F is going to become Fg, which is equal to mg, because force, according to Newton's second law, equals what?
I missed the question. Can you repeat it?
Yes. So I'm going to try and find the work due to gravity. Now, that means that our force F in our work equation, if we're trying to find the work due to gravity, is going to be the force of gravity, right? And force equals mass times acceleration, according to Newton's second law. And in this case, our acceleration is going to be g, because we're finding the work due to gravity, which means that m, 4 kilograms, times g, 9.8 meters per second squared, times our distance or displacement of 12 meters, times cosine of theta. Now before I write theta, can someone tell me what theta is? If this force is going straight down and the direction of motion is directly along the x-axis horizontally,
Cosine of 90 degrees.
cosine of 90 degrees. Now, what does cosine of 90 equal?
I forgot.
That's okay. So cosine of 90 degrees is going to equal 0.
Oh, yeah, okay.
Alright? So if I write cosine of 90 degrees, well, this can just reduce down to 0, which means the work due to gravity is simply 0 joules. Does everything seem okay so far?
It's good to me.
Alright. Now, let's try and calculate the work for the normal force. So the normal force, in this case, Wm for normal force equals the normal force, which is just going to be N, because in this case, that is the force we are looking to find the work for, times a distance of 12 meters, and again, just like with the force due to gravity, this normal force is going to have an angle of 90 degrees with respect to the direction of motion. And we said cosine of 90 equals 0, which means the work due to the normal force is also going to be 0 joules. Does, yes.
Is the normal force always equal to the weight?
No.
Is it equal to the weight in this case?
No. In fact, I was gonna.
You're probably getting there. Sorry.
So now, there's another force that I want to calculate the work for, and that is the force of kinetic friction. Now, if I want to find the work due to kinetic friction, that would equal the force of kinetic friction times our distance of 12 times our cosine of theta. Do we remember what the formula is in order to find the value of kinetic friction?
It's the normal force times the coefficient of friction.
That's right. So we have our coefficient of friction of 0.2. I'm gonna do this work over here. So Fk equals coefficient of friction, which is 0.2, times the normal force, N. But that means, yes.
I've got a question for you,
Yep.
an honest one, in your experience. Have you seen different notations for like ways of expressing forces? Like you express the normal force as capital N. I would express it as a capital F with a subscript N. Have you found that there are different notations in different textbooks and different resources?
Yeah, often on I forgot the name of it, but the textbook that we read through online for Michigan Virtual often denoted the normal force as just an N.
Okay, fair enough, but you see that depending on the textbook you're looking at, some will denote it as an N, others will denote it as a capital F sub N.
Yep.
So there's different notations for the same idea.
Same as like the, like,
Frictional force,
Yeah.
I would label this as a capital F with a subscript little f, and that, so there's just different ways of writing the same thing.
Mhm.
So, all good.
So now that means that I need to find the value for my normal force. Now, as I sort of said earlier, if this object is not accelerating vertically, what can we conclude about the sum of the forces vertically? What does it equal? Yes?
0.
0. So the sum, are you guys, I don't really know, are you guys familiar with this sigma notation? Okay, I just wanted to make sure. So the sum of the forces,
Oh,
F1,
oh, sorry, I just
Oh.
asked you a question.
sorry, equals 0. Now, I'm sorry if I'm asking you guys a lot of questions. I just kind of want to, not just go through everything myself. I feel like it's good to ask a lot of questions.
I agree.
Is someone able to tell me what the vertical forces influencing this object are? Yes.
So there's the force of gravity in the downward direction,
Mhm.
the normal force in the upward direction, as well as like the y, I forgot what it's called, but of the F
Talking
equals
about this?
50, yeah,
Yes.
so like y portion of that force.
So let's add a little line here. And like you said, let's just call that y. That's our y component.
And that's the word.
That's
think
the
you're
word, I
looking
forgot
for,
the
is
word component, I said
component.
portion,
Yeah.
I meant component.
Yep.
Mhm. So if the sum of the forces in the y direction equals 0, that also means that the sum of the forces in the y direction equals n, or f sub n, as Mr. McDonald stated, minus mg. And then we also have this value for y. And using some trigonometry, you're able to find that value for y. If the sine of 30 degrees, because we said theta equals 30 degrees, the sine of 30 degrees would equal y over this value for f, which is 50, correct? Because this is 50, the hypotenuse, right? So, sine of 30 degrees equals y over 50. If you multiply both sides by 50, that gives you 50 sine of 30 degrees equals y. And the sine of 30 degrees is simply equal to 1/2. So that's the same thing as 50 times 1/2, which is 25 equals y. 25 newtons. So now that we know that y equals 25 newtons, we can say that the sum of the forces in the y direction equals N minus mg plus 25 equals 0. Now, we want to solve for n. That's what we've been looking for this whole time. So, I can simply say that n equals, well, I can add mg to this side, and then I can subtract 25. So n equals mg minus 25. We set our value for n is 4 kilograms. G is 9.8 meters per second squared. 4 times 9.8 is 39.2. I want to make sure I did that right.
That's correct.
39.2. Which equals 39.2 minus 25, which equals 14.2 newtons. So now that we have our value for n, we can plug that in right here. 0.2 times 14.2 newtons for our normal force equals 2.84. So the value for Fk equals 2.84 newtons. And now we're on to our last step.
How do you get 2.84?
Because-
0.2 times n, where n is equal to 14.2?
Yes.
Alright.
So now that we have our force of kinetic friction, we can plug that in right here. So that means the work done by kinetic friction equals 2.84 times our distance of 12 meters in which the object travels times cosine, and again, before I write theta, since the direction of motion is this way, and friction is acting in the opposite direction, what's the angle between the force and the direction of motion? Yes, 180 degrees. Is someone able to tell me what cosine of 180 equals?
-1.
-1, yes. So when we multiply this by cosine of 180 degrees, we can reduce that down to -1, which is simply equal to negative force times distance, which in this case would be negative 2.84 times 12 which is approximately negative 34 joules. So because this value for work due to kinetic friction is negative, that means it's taking away from the energy of this block, the kinetic energy. Yes?
If you were to break the unit up into its parts, and I think that was one of Abe's first question, like if you were to take a joule, what are the pieces of the joule? Like,
Kilogram or something with newtons.
yeah, what?
Isn't it Newton meters?
So I think if we're looking at the, yeah, I mean, if we look at the force equation, like you get a joule because you take a Newton multiplied by a meter.
Mhm.
So a joule then must be a Newton times a meter,
Yes.
right? Because what if I divided a joule by a meter?
Mhm.
What do I get?
Mhm.
I get a Newton, right? So I don't know, I was just asking like, so I think at least one way of breaking up a joule is to say it's Newtons times meters. That helps us a little bit.
Yeah.
Go ahead, oh, sorry, yeah.
So now, we have our work done by this force F, 520 joules. The work done by gravity and by the normal force, both 0. And the work done by kinetic friction is negative 34 joules.
Question.
Yes. Oh, yes.
Should we, like, I guess we don't need it here, but like if we were asked, like, what's the net force in the x direction or something, we should find, like, Fx, or the component, the x component of the 15 newton force, right?
Yeah, you want to find the value of the x component. If you were just, if we replace this with an x, yeah, you would only want to pay attention to forces acting in the x direction.
I guess it's kind of back to you. Did we do that already? Like, did you look at, was there one of these things up here that does take the x component of the applied force F? Was there a work that was found that was based on the applied force F? So did we do a work about F? Is there a W sub F up there?
Yes.
When you solve for W sub F and you use the force 50 and the distance 12, notice the cosine 30 actually is the component of F in the x direction,
Oh, yeah, okay.
right? I think you're also talking about the net force,
Yeah,
and I'm sure Frank's kind of getting there as well, so.
In fact,
You're good.
that's actually what I was about to just do right now. Because the reason I wanted to find all these forces was so I could now find the net force of this block. So I'm gonna move over here. Excuse me, sorry about that. I'm gonna move over here now. So net force equals the sum of all the forces acting on that block. So with these forces we have, that means W net equals WF plus WG plus WN and then plus WFK. We said that WF is equal to 520 joules, WG is 0 joules, W sub N is 0 joules, and then W sub F sub K is negative 34 joules. So that means the net work done on this block reduces down to 520 joules plus a negative 34 joules, which is just minus 34, which equals a net work of 486 joules. Do we all understand that? We're just adding up all of the work done. Alright. Now, as I'm sure you also have touched on, net work also equals a change in kinetic energy. Alright? And before I move on, I really wanted to maybe answer a why question. Not just telling you that force or network equals changing kinetic energy, but showing you why that is. So I'd like to do a quick, simple derivation, if that's okay.
That's lovely. I actually think that this is a key part that I think that needs some help with a good explanation. So do your thing. I think a derivation would be good.
So, network equals change in kinetic energy, delta KE, which equals 1/2 mv sub F squared, that's the final velocity, minus 1/2 mv sub I squared, that's the initial velocity squared. And now let's also go back to our work equation over here. Let's just assume that the angle between the force and the direction of motion is 0. So that way, cosine of theta just equals cosine 0, which is 1. Cosine of 0 is 1. So in that case, work would simply equal force times distance. Are we following that? So, like I said earlier, what is Newton's second law? Yep, go ahead.
F equals ma.
F equals ma. So what can we change this F to?
Ma.
Ma. W equals force times distance equals MAD. Now, by the way, before I continue, theta could be any angle, and this derivation still works. Just to keep things simple, I just want to make the angle 0 so that way we get rid of it. All right. So W equals MAD, and I actually see this equation right here. VF squared equals VI squared plus 2AD. We have an AD and we have an AD up there. So let's isolate AD over here and see if we can substitute the value we find for AD to be equivalent to in for AD over here. So you guys see what I'm gonna do? Alright. So VF squared equals VI squared plus 2AD. If I subtract the VI squared from both sides, I get VF squared minus VI squared equals 2AD. Now I have to divide both sides by 2. And if I do that, that's the same thing as multiplying by 1/2. So now I'm gonna have 1/2 times VF squared minus VI squared equals AD. So notice, 1/2 VF squared minus VI squared equals AD. I can distribute that 1/2, which equals 1/2 VF squared minus 1/2 VI squared equals AD. So, when we solve for AD in this equation right here, we figure out that it equals 1/2 VF squared minus 1/2 VI squared. So now, as you can probably see what I'm about to do, I can plug in this new value for AD in here. So now, work equals M times 1/2 VF squared minus 1/2 VI squared. If I distribute the M, work equals 1/2 MVF squared minus 1/2 MVI squared. And notice that equals changing kinetic energy. So I didn't do this derivation just to do a bunch of math, a bunch of algebra and be confusing. I did it because I feel like, again, answering that why question, why work can also equal changing kinetic energy is really important, and it's not just in physics. I think understanding why is important in anything that you do. I feel like there's more value in knowing why something is what it is, rather than just being able to do it, but not having the intuition, right? So now, with this idea of change in kinetic energy, let's say our block over here starts from rest, right? It's initially at rest. And we said the net work equals 1/2 MVF squared minus 1/2 MVI squared. If it's initially at rest, it has no velocity, that means this VI squared is just 0. 1/2 times m times 0 squared is 0, right? So that means the net work that we calculated of 486 joules just equals 1/2 MDF squared, if it starts from rest, all right? So by just knowing that this block has an initial velocity of 0, it's initially at rest, I'm able to find the final velocity of this block at the end of its journey. So if I divide both sides by 1/2, that means I'm multiplying this side by 2, which is 972 joules equals MPF squared. Actually, let me get rid of this real quick. Let me get rid of this joule symbol. We said that the mass of our block is 4 kilograms. So that means 972 equals MDF squared equals 4VF squared. So I want to divide 972 by 4, which is 243. Equals VF squared. So now if I want to find the final velocity, I simply have to find the square root of 243, which is about 15.6 meters per second equals V sub F. So just by, again, being told that the block is initially at rest and it has an initial velocity of 0, with the values I already have, I'm able to find what the final velocity of this block should be at the end of its 12-meter journey. Yes?
The step where it says 243 equals VF squared,
Mm-hmm.
what are the units on the left side of that? Like basically the step before, you take joules and divide by kilograms. What units do you have there for 243?
That would be, so that's joules per kilogram, which
It
would
would
be,
be joules per kilogram, which is a Newton meter divided by a kilogram. So it's a Newton divided by a kilogram times a meter. So if you take a Newton and divide by a kilogram, what do you get? If you take force divided by mass.
acceleration.
You get meters per second squared. If you take a meter per second squared, you multiply by another meter. Meter squared per second squared. So in that 243, you're in units of meter squared per second squared, which is equal to V squared, which is what we assume is true.
Mm-hmm.
Yeah.
All right. So, again, I'm gonna ask, does that make sense? All right. If not, that's okay. Physics can be confusing, but I feel like, I mean, if someone just walked in, they might see all this and it might be confusing, but when you start from step one and you go to the final step, it's really, I'm gonna be honest, it's really not as difficult as some people want to make it out to be. All right, it really isn't. All right, it's just algebra. Now, I would like to end what I'm doing with just a few examples, if that's okay,
Yeah.
in which I'd like you guys to spend just a couple minutes solving the problems. And they're not gonna be super difficult, they're just basic work-related problems. So this first example I have, I'm gonna do my best to draw a hot air balloon. It's probably not gonna look like one though. Let's say, that's my hot air balloon.
Perfect.
Exactly. Let's say it's moving in this direction. 50 meters. And there is a force of wind of 200 newtons acting on it. What's the work done by the force of wind? That's all it is. And I don't know how long this is necessarily going to take, but if someone has an answer, please feel free to say it.
10,000 joules?
10,000 joules. Good. It was simply just 200 times 50, right? Because the direction of motion is in the same direction as this force. So work equals force times distance. Cosine 0 is 1. That's 200 times 50, which is 10,000. So that wasn't hard, was it? No? Yes?
I think the direct application is pretty well understood, right? Applying the equation, I think is good. You had some good questions the other day where you were asking, and I was having a harder time explaining. Like, I think would be a good idea, my opinion is, if you ask Frank questions that you actually truly want to ask. Like, there's some like, what about this, that, or the other? Like, change up the situation to whatever you are thinking about. And just address that to Frank, and he'll give you an honest answer.
I hope I can answer your questions.
And it's fair enough to say I don't know.
Mhm.
I think that's a fair question, or a fair response to a reasonable question. But you all had some questions that you care about, that you're wondering about, and just, I think, voice that. So, what's your question?
If the hot air balloon had a mass, how would we go about finding its normal force? Do we have to like assume that that air balloon is on one plane?
So if the hot air balloon is in the air and it doesn't have an acceleration upward or downward, it's just moving in this horizontal direction, then that means the force going upward would have to counteract the force due to gravity, mg, because it doesn't have any acceleration upward. So that means that it would be equal to mg. Is that correct?
So, what I would say is, what I would ask you is there a normal force here? Is there a normal force present in that scenario?
Is it necessary or like every?
I'm just asking a question. Is there a normal force present? I disagree. Okay? You are, I think, are responding to like, is there necessarily an upward force? The answer to that is yes. Is there necessarily a normal force? My response to that is no. In fact, there is not a normal force here, because normal force is specific for a particular application. That application is not present in the air balloon, it is present in the block. It's not sitting on a surface, it's just floating in the air. Now, does that mean that there's not an upward force? No, it doesn't mean that there's not an upward force. There is an upward force. How do we know that there is an upward force? Because it's not falling. That's how we know that there's an upward force. And what is that upward force from? What does it come from? Hot air, right? And so there's some sort of lifting of force. And how does it balance out with the gravitational force? It totals to zero. They're exactly equal to each other. There is often questions about like, isn't there actually air resistance here? And we're saying like, well, we minimize the air resistance stuff and we just call it a net force. So you might assume that there's some air resistance there. There may actually be some, but I think Siri says F wind. We could say also maybe there is some air resistance force in the opposite direction. We total those up and we get a different number. Question.
I was just gonna ask, do you think physics like allow like air resistance?
Yeah, there's.
Factor that into like a
Yeah, we started pretty basic, but then we incorporated other elements such as air resistance to make things more realistic.
Frank, you just completed AP Physics C, a calculus-based AP Physics class that focused all about motion, right? All about mechanics. If you were to say, there's this one skill set that, or there's this one area where this is where the problems arise. Where are the issues?
For most students or for myself?
For most students, and maybe I would toss you into that as well. Like, if you're working through a problem and you're trying to get an answer, and sometimes you don't get the answer, what goes wrong? How does that process break down? What is the most common place that errors arise?
Well, me personally, I would, maybe this is just because this is how I was when I initially, took physics a while
Yeah.
back.
So you.
I had a tough time sort of identifying the multitude of forces that could be acting on an object. Just for example, up there we have F equals 50 newtons, but there's also that component of Y, there's that component of X, there's, hidden variables that you need to consider with that.
Yeah.
And for me, that's something that I kind of would overlook on occasion.
Yep.
I would just assume N and mg are the only forces acting in the vertical direction. Back in the day.
Have you all, do you think that you've increased your capability of just identifying that although there's a force F is 50, that's not the whole story. There's a lot of other stuff going on. I was trying to lead you into what I believe to be true, which is the most common place that mistakes are made. The most common place mistakes are made? Algebra. Agree. Even for you, whose algebra is pretty tight, and your work looks really good. Still, that's where mistakes are typically made. So.
Yeah, no matter who you are, no matter how good you think you are at physics or math, just one little mistake somewhere is going to alter the final answer, and it could make your answer way off or a little off, but either
Yeah.
way,
Yeah.
it's still off.
So accounting, organization, and accounting is as important as all of the physics principles as well.
Mm-hmm.
Cool. So 10,000. You got another example?
If that's okay, could I do one more?
I would love that.
All right.
And I really appreciate you being here, so you're doing a really good job.
Thank you.
It's not easy to do, folks. Not easy.
Now, would you rather have a work due to gravity or a work due to tension?
We haven't dealt much with tension. So let's do tension.
Sure. Do what he wants. Yeah, I like that. That's cool.
Because that's actually due to tension and it is going upward.
Mm-hmm.
All right, so that's good.
So my artistic skills, I'm going to draw a block. In fact, I'm going to make it the same block as over there. I'm going to say that M equals 4 kilograms.
Beautiful block.
Thank you.
It's a really high quality block.
And this is my sort of pulley system. This block is moving upward at a constant velocity of 2 meters per second. There's also a force of mg acting on this block. So what I want to find is, due to tension, what is the work due to tension in 5 seconds?
We had a question.
Yes.
I was just wondering, is there like a notation that you use for constant velocity?
Constant velocity.
Yeah, so like, if you said this is a constant velocity, if I wanted to write that down and show that somehow, is there like a specific notation that you use?
I've always just written constant velocity. Is
Okay.
there like a notation for just saying saying constant velocity?
I mean, the notation I would use to identify that it is constant is just V, right? So V represents velocity. If I use VI and VF, I'm like saying that it's changing. And if I don't use I or F, then I'm basically kind of stating that it's
Okay.
not.
Okay, I just didn't know if there was a.
Yeah, there's not like a standard, like, that's more like the context of the problem and the story and stuff like that, but just V indicates that it's not, there's no change between the beginning and the end.
So again, I have my block, which is 4 kilograms. It is moving up this pulley at 2 meters per second. So the work due to tension in 5 seconds equals what? And again, just take your time, and if you think you have an answer, feel free to just say it. I'd love to hear it.
What do y'all think time has to do with it?
Displacement.
Right, so I think that's sort of like leading us down the path that if it's moving at a speed for some time, that's the distance it's traveled. So we're taking that information, we're extracting distance out of speed and time.
Is there an equation for attention force? Something other than,
So, in this problem in particular, tension equals something else that is present in the problem. I'll just say that.
There is not like a specific equation for tension. Tension is just a type of a force that could be acting on an object in some locations, in some applications. So it's dependent on the context of the problem. You know, if you think of the tension force that, like a rope that is attaching a sail to a sailboat experiences, it varies, right? Depending on how hard the wind is blowing, how fast the boat is moving, the tension in the rope that's connecting the sail to the sailboat itself is gonna change, you know, quite a bit. So how we define that force is different for everything. And a sail force would have a very odd looking function that relates its ability to hold sail of the boat. Yeah. With F though, what are you using for F?
I didn't,
Oh, you're solving for F.
but then,
Okay.
and then I tried to, so, I mean, it doesn't even make sense, so. But, another.
Gotcha. Why don't we, I mean, we're running short on time, so why don't you give Frank some insights and kind of maybe follow your lead and we'll see what.
the network is 0, right? Because it's moving at a constant velocity. But then we're just trying to find the work done by the tension of the string.
Yes.
Is that just 392 joules?
Yes, it is is. Now, instead of me explaining, could you explain what you did?
Yes. The forces, it's moving at a constant velocity, which means the change in velocity is zero. So we know that the force pulling up is the same as the force pulling down. So the tension force is the same as the force of gravity, which is mass times g. So when you do 4 times negative 9.8, you get negative 39.2. And then if you do force times displacement, you get work, then you get, and to define the displacement, we know it's traveling at 2 meters a second for 5 seconds. You just do 2 times 5, which equals 10. So it traveled 10 meters, then we can do 39.2 times 10, we get 392.
Yes. So, like he said, this is moving at a constant velocity. The acceleration is 0. Mass times acceleration, mass times 0 equals 0. So that means force, sum of the forces in the y direction equals 0.
And Danny, your question, and I was saying, how do you express like constant velocity by saying v equals 2 meters per second? The statement here, the right side of the equals 0, is an extension of the acceleration is equal to 0, right? I think that's actually the other notation of how the velocity is expressed as being constant. It's expressed as being constant when the acceleration in that direction is 0. So a is 0.
Yep. And so the force is acting in this y direction would be tension, and the force of gravity mg. Tension minus mg equals 0, which of course means our force of tension equals mg. We said m is equal to 4 kilograms and g is 9.8, and we said earlier that that is 39.2 newtons. So that means T equals 4 kilograms. And then we have our 9.8 meters per second squared equals 39.2 newtons. And since tension is working in the same direction as the motion of this block, that means our cosine theta in our work equation is going to reduce down to 1, because cosine 0 is 1, right? So that means the work simply equals force times distance. And I'm sorry, what's your name?
E.
I'm sorry?
Abe.
Okay. As Abe said, if it's moving at 2 meters per second for 5 seconds, it travels a distance of 10 meters. So that means the work done by the force of tension equals the force of tension, 39.2, times our displacement of 10, which equals 392 joules. So that's the work done by tension in this scenario.
It's awesome. Did I ask you a question? This right here, would you ever write that down floating out there by itself? How do you know that this is true?
I know it's true because, like, up here, some of the forces in the y direction is 0, and I know I have T and I have mg.
You know all of that. Would you ever write this down without writing this down first?
No.
A point of note. So, and the other question is, like I have for you, is T equal to positive 39.2 or is it equal to negative 39.2?
Equal to positive.
It's equal to positive 39.2, but you didn't say that. And if you have T equals mg written down, which you do have, and I haven't looked at all of theirs, that comes from somewhere. So don't skip this step. Like maybe the most important step, and I would like your opinion on this, is this step right here.
Mr. McDonald has said that Newton's second law, F equals ma, is the most important equation in physics, and this is Newton's second law, mass times acceleration.
And it's not a whole lot of work, and it's super duper important. And in my opinion, don't skip this step. Because you cannot possibly do the more complicated stuff if you skip simple steps like that. And if you want to do fun and interesting things that make a difference in the world, like you're not going to be analyzing a box being raised at a constant velocity on a pulley. Like that's not what you're going to be doing in the real world. You're going to be doing something far more complicated. Do yourself a favor, don't skip that step. All right. Other
That's it.
questions?
Yeah, that's it for me. If you guys have any questions, please feel free to ask.
Now's the time. Fire it. Fire it at him. Stump him.
Well, no, it's not like, I don't know why I did this, but I didn't even factor in energy when I was trying to solve it, and I just did F times D, like I just pretty much did work equals kinetic energy, and I just wrote it out, like F times D equals 1/2 mv squared, and I knew that it was a constant velocity, so I plugged in D squared, like 2 squared, and then I had mass is 4, so then I got like 4 16 times 1/2 is 8. And then the other side, I already figured out distance, which was 10. So then I did F times 10 equals 8. So I divided by 10 on both sides. I got 0.8 equals the force when I was trying to solve it, which obviously isn't correct. But like, what makes that not correct? And then I did it a whole different way. I got the answer, but I don't know why I did that at first, but I don't get why it doesn't work.
Because so we would have to, so this is not work equals a single kinetic energy. This is that the work equals a change in kinetic energy.
Yeah.
And how does the kinetic energy of that object change?
Well, I thought since it wasn't, it's a constant velocity.
It is a constant velocity, so that means all of the kinetic energy at the end minus all of the kinetic energy at the beginning is all minus all equals none. So the total work done doesn't equal 8.
Oh, yes, okay.
It equals nothing,
Okay.
right? And so what do we have here? Then we have 392 units of work that's doing the upward stuff. Okay, 392 units of work in the opposite direction doing the downward attempt, right? And we sum up the work done by tension, so work done by gravity, and what do you get? Nothing, right? So it's the right side of your equation.
Oh, yeah, makes sense.
Other questions? You had some like constant, like, don't we accelerate, or we were talking about like an up and down moving thing. I don't know if you have any.
Oh yeah, it just kind of like intuitively doesn't make sense to me that like, what was my question?
Like we're looking at a problem like this, and it
We're
was like
talking about
moving
downwards
upwards. So, and
motion.
I don't know if you've struggled with this. Like when this is moving upwards, we assume that it was at rest in the past, and it accelerated to move from 0 to 2 meters per second, which would mean that it has a non-zero sum of forces. And so we kind of get into that, like, what's up with all of that stuff? But I think that we have to just like accept that it was accelerating in the past, and now it's not.
Well, no, my thing was that, I think it was that we were looking at like something with a constant velocity,
Yeah,
and work was 0, which made no sense to me.
which is this. There's no
Right.
work done here.
The problem that we had.
There is this amount of work done by the string, and there's the exact same amount of downward work done by the weight, and the sum of all of the works is,
It's just weird.
But it's
Nothing.
moving, so it
and the
doesn't make
work is zero.
sense.
If
But
you
it is
would,
moving, so it doesn't make a lot of sense.
clap it up for this guy right here. Good job, well done. That is not an easy thing to do, and
That's very good.
I think that you really,
I appreciate you guys being such a great audience.
What do you want to do?
you did a fantastic
You
job,
don't
bud.
want to be a teacher ever, an astrophysicist.
gonna be an astrophysicist.
But you don't, like,
I think the problem we had was picking a box. So we were just like that box.
Yeah.